Now let us discuss the different situation. In the last section, we discussed the interference of two waves that move in the same direction but with the different phase constant. Now, if we look at the two waves that move in the opposite direction, but other than that, these two waves are identical. For example, if we have two speakers that create two identical sound waves, but the sound wave move in the different direction like this. So what we want to see now is that what is the result of the interference of these two waves. So if we write down the wave function of two waves, the wave number 1, y1 is equal to a sine kx minus omega t, and the second one is a wave that moves in the opposite direction, so we can write it as y2 equal to a sine kx plus omega t. For our convenience, again, we will assume that the amplitude of these two waves are equal and it has the identical value of k and omega, but only the direction that different. So the superposition of these two waves, y is equal to y1 plus y2, which is equal to a sine kx minus omega t plus a sine kx plus omega t. And using the trigonometric identity, sine of a plus or minus b is equal to the sine a cos b plus or minus cos a sine b, cos a sine b. Okay, and apply this identity to the first and the second term. We have plus and minus sign, and after the algebraic manipulation, we will have that the resulting superposition y equal to y1 plus y2 is equal to 2a sine kx times cos omega t. It is interesting that the resulting of the superposition of these two waves does not have the form of the traveling wave, but it has the form of just the oscillation, the simple harmonic motion, with the different amplitude that depend on the position of the oscillation. We call this form of the resulting wave as the standing wave. Standing wave. Okay, the word standing means that it's not move, but it's oscillate. it has the shape of the sinusoidal wave that result from the oscillation of the medium, and the amplitude of the oscillation depend on the position of the oscillator. We can explain the formation of the standing wave as follows. We are looking at two waves that move in the opposite direction. Okay, the first wave move to the right, the blue wave, the green wave move to the left. At the instant that these two waves are in phase here means that if the first wave oscillate upward like this, the second wave oscillate upward too, and this will give us the perfect constructive interference. So at this instant of time, we will have the resulting wave like this brown line. Next, when the blue wave move away from this position and the green wave also move away from this position, we will have this situation that we will have the instant that the blue wave and the green wave are out of phase. The out of phase here means that when the blue wave, the displacement from the blue wave go upward like this, the displacement from the green wave go downward like this. So in this situation, the interference is perfect destructive interference, and the resulting displacement of the medium is equal is zero everywhere at this instant. And you can see that after that, when the blue wave move away to this position and the green wave move to this position, again these two waves are in phase. It means that the displacement from these two waves go in the same direction. So we will have the wave like this. You can see that the resulting wave does not move, but it oscillates up and down, and the amplitude of the oscillation depends on the position on the medium. At some position, like at this point that have the letter N like this, we call it the node. This is the node of the oscillation. The position, the node position, will give no oscillation at all time. And you can see that at this time, this position has no oscillation. This position, this position, this position, and this position. And at this time, everywhere there is no oscillation. And after that, we again have that this position has no oscillation. On the contrary, you can see that some position that we denote by the letter A, which A stands for the anti-node. Which it means that at some position like here and this point A, this point and this point, the oscillation will have the maximum amplitude the oscillation will have the maximum amplitude. Okay, so you can see that this is the maximum displacement of the medium, and then it goes to 0, and then it goes to the maximum in the negative direction. So we have the node and the antinode, but the most important is that this pattern does not move, but it oscillates with a different amplitude at a different position. This is an example of the real standing wave on a string, and we will discuss this in more detail later, but you can see that when we have the standing wave, we will have the position that the oscillation has the maximum amplitude, which we call it the antinode, and the position that there is no oscillation at all, and we call it the node. And we have the node, antinode, node, antinode, node, and antinode and node, something like this. Okay, now let me go to some mathematical description of this standing wave. Looking at this expression again, you can see that this term gives us the simple harmonic motion, which means that it gives the oscillation of the medium at each point. And this term gives us the amplitude of the oscillation. You can see that the amplitude of the oscillation is a sinusoidal function of the position with the wavelength equal to the wavelength of the original wave. Okay, so when we look at the standing wave, like in this figure, we know that this is the wavelength. This is the wavelength of the amplitude, and also it is the wavelength of the original wave. So we have that this is equal to lambda. So from this we can see that at the position x equal to 0, x equal to the half of the lambda, x equal to the lambda, and so on, we will have the position of the node. So we can have that from this expression. We will have that the position of the node is at x equal to 0, x equal to lambda over 2, x equal to lambda, x equal to the 3 lambda over 2, and so on. Or in general, we have that at the position of x equal to the n lambda over 2, where n is equal to 0, 1, 2, and so on. Okay, this is the position of the node. For the position of the antinode, we have that if we look at this figure again, this is the position of the antinode, which equal to the lambda over 4, and this is the 3 lambda over 4, and so on. So we have that at the position of x equal to lambda over 4, 3 lambda over 4, 5 lambda over 4, and so on. Or in general, we can have that at x equal to n lambda over 4, where n equal to 1, 2, equal to 1, 3, 5, and so on. We will have the position of antinode. Okay. From this expression, we can have that the distance between adjacent antinode is equal to lambda over 2. Also, the distance between adjacent node is equal to lambda over 2, 2. The distance between node and an adjacent antinode is lambda over 4. Okay, so that is the description of the standing wave.